Good morning, everyone. Welcome to a Savvius webinar. Today's topic is Troubleshooting Unified Communications. I'd like to introduce today's presenter, Jay Botelho. He is the Director of Products here at Savvius. Jay, I'm going to go ahead and turn it over to you.
Thanks, Matt, and welcome everybody. Thanks for joining this morning for one of Savvius's many regularly scheduled webinars. This morning's topic being on troubleshooting unified communications. So without further ado, I'm just going to jump right in, show you the agenda. So I get my slides together. There we go. So topic today, of course, is unified communications. It's a very broad topic, of course. What we're taking today is a perspective of it from troubleshooting and from a network troubleshooting perspective. I know that it's relatively specific, but I think that's really the right way when it comes to troubleshooting unified communications is over the network. So some of the main topics we want to cover today is number one, I'm just going to go through a quick definition just to make sure we're all on the same page, but then just wanted to show you a few stats that give you the idea that even after all of these years, starting way back with VoIP, and of course unified communications has evolved a long way since then, that it's still top of mind in terms of network performance. Apparently still lots of issues around unified communications, hence the need for detailed troubleshooting at the network level. I want to talk a little bit about just the real-time aspect of UC specifically, and just how it is different from other types of network traffic. I mean, it's really a key point. I mean, if you take nothing else away from this today, I think that's the key point to take away, that when you're looking at VoIP, when you're addressing VoIP or unified communications in general, things are a little bit different. I want to talk about, along that same line, how UC and other types of traditional data on the network coexist. I want to spend a few minutes just talking about UC over Wi-Fi, because that's becoming even a more common use case, and it does have a few unique issues of its own. And then just very quickly at the end, although most of this is quite generic to unified communications over the network in general, I just wanted to show you a real quick demo of some of the ways to get at some of the statistics that we're going to talk about in this presentation from within our network analysis solution, OmniPeak. The one other thing I just wanted to mention quickly as we go is I may often slip and say VoIP versus unified communications. That's not to say that I'm saying that all unified communications are just VoIP. They're not. It does happen to be still the most common one, and it's also one of the easiest ones to draw the analogies with. So I am going to use VoIP a fair bit through here as an example of unified communications, but pretty much all of the points we're making within here pertain to unified communications. So, as I said, start with the definition, and what is unified communications? Well, I went from two different perspectives, right? First, I went to just what do the industry analysts say? So this comes right from the Gartner glossary, as you can see. I'll let you read it. It's it's relatively straightforward, but at the same time, when I read this definition, it didn't really resonate with me. I was like, what does that really kind of all mean? I get it, but I kind of don't get it. It doesn't really tell me all that much. So then, of course, I turned to where we would all turn, to Wikipedia, and liked this definition better just to begin with, because even though marketing is part of what I do as head of products, it talks about UC being a marketing buzzword, which in some ways it is, right? Because it's used to describe a very large set of things. But at least in the case of the definition from Wikipedia, it does go on to give some very detailed examples of, what is considered from their perspective to be part of unified communications. And I thought that was very useful, right? But even more useful from my perspective, because I said I'm taking a network perspective to this, right? What is the impact of unified communications on the network, and what is the impact of the network on unified communications? And what I liked about the Wikipedia definition is, it really brought out those terms, and I highlighted them in red because there's an awful lot of words in their definition, but, basically it's described as the integration of real-time with non-real-time communication. And although they're talking about the forms of communication themselves, right, a voice call versus email, I thought this was interesting because it also brings about and highlights exactly what is the issue on the network side as well, right? Unified communications, to me, when I think of unified communications in terms of having that on the network, I think of the real-time parts of unified communication, because that's what makes unified communication, VoIP, video, etc., different from your other network traffic. So I'm going to use this distinction of integration of real-time with non-real-time communication to highlight the difference between unified communication in general on the network and general network traffic. Being a little more specific about that, what I kind of mean is, when for the real-time, parts of unified communication, voice, video, etc., there is a real need for the data to be transmitted now, not later, and now and later, I'm talking milliseconds now later, not seconds now later, but even at that level, and we're going to talk more about this, the data needs to be delivered right now. There's an urgency to the data. My voice has a cadence to it. There's all the syllables fit together in the right order to form words, and words that other people understand. And if I try to take some of those out of order, or I just don't get some of that information at all or in time, I can't insert it back in and have it be the same conversation that I started with on the phone. So the data has to come now rather than later. Another way that I like to think about it, kind of coming from an engineering background, is, what's the source of the data that I'm dealing with? If the source of the data, the communication was analog, which would typically be in my voice or video, right? Movement. That's all analog, right? There's nothing digitized about it. We digitize it to move it around on the network, but it's analog, right? It's fluid, it's continuous, and that to me is the biggest distinction to think about when thinking about this unified communication data on the network. If it was analog to begin with, it is therefore going to need to be dealt with in real time. If it's digital, not that you can wait forever, because there's just user experience issues and other things behind that. But once data's been digitized, and especially if it's just like a transfer of a file or something, things can come out of order. Things can come out of order by even a fairly significant amount of time. It's just a matter of buffering and putting things back in the right order, and the user may not even notice a half-second delay. Whereas, as you see, as we get a little further on here, a half-second delay in voice is critical. It basically doesn't even fit back into the conversation then. So just quickly shifting gears just for a second, I wanted to just give you a little bit of a perspective of how unified communications is still top of mind for network engineers, IT engineers, and network performance monitoring in general. These are some stats that came from some research from an organization called Track Research. It is a few years old, but it highlights, really the way things still are today, and shows, shows the situation from two perspectives, and that's what I like, because it's two slides back to back. So the first in the survey, and it was a survey of about 400, just a few over, like 405, IT professionals. And they were asked, what are the key challenges for managing UC performance? So a direct question that pertains to exactly what we're talking about today, unified communications. And you see that their top challenge was visibility into the impact of UC on other applications on the network. So definitely, straightforward and exactly kind of what you'd expect a concern to be. Maybe not be their top concern. That's over, user experience and over bandwidth and, et cetera. So, it's obviously top of mind for them. But then the report also takes the question and kind of, turns it on its head and says, well, what are the challenges for managing network traffic? And, the first thing that comes back is, well, managing the real-time applications, basically, managing the real-time end of unified communications, VoIP, video, et cetera, is their key challenge. So we see that unified communications rises very much to the top in terms of challenges for network engineers, and it doesn't matter what your perspective is, whether your perspective is the network or whether your perspective is the unified communications itself. It's a key challenge regardless. So let's get into this just a little bit more about how the real-time communication is different. Right? How are this network data, these network packets that are part of unified communications, how is that different from my traditional, FTP file transfer, for example? Well, couldn't think of a better way to show this difference than to show some packets, because that's part of what we do here at Savvius. Is we deal with analyzing networks from a network and from a packet perspective. So what I'm showing here is just two small snippets, screenshots from both a data stream and a VoIP stream. So what we're looking at is line by line or row by row is a snippet of a decode of individual packets, and I only snipped out those columns, the delta time, size, and the size bar, which really shows the type of data in the packet, just to highlight a few points. Of course, there would be a lot more data for any given packet, but these are the columns that really are able to highlight what I feel are some of the key differences between something that's real time and something that's maybe not necessarily as real time. So starting first at just the type there, just to prove the point that we're comparing data with VoIP, I've highlighted one end of that size bar, which starting on the VoIP end, you can see that that's all G.711, and G.711 is a very common encoding and decoding scheme for voice over IP, extremely common. You can see that that's what all of those packets are, and that's typical of a VoIP communication. Now, typically if I were monitoring or collecting the packets from a large network, I'd see other data interspersed within there. For the purposes of this illustration, I filtered down to a particular flow, and because that flow is already into the communication part of the call, we're past the messaging parts of the call. We're seeing just the data, and that's what we'd see. That's how we would see the G.711. On the data side, you see the actual application itself is called TDS. You see some packets with that about midway down the screenshot, and you see there's some other messaging that goes along in there in that conversation. There's several things going on in that conversation, but you see that is just traditional application data. So starting to highlight some of the key differences. Well, first, moving to the left, in that size bar, now we're looking at the actual protocol itself that was used, the layer 2 protocol used to send the data. And we see in the case of data, I'll start on the right this time, it was all sent over TCP. Right, and in the case of VoIP, it actually uses a different protocol. Right, it uses UDP, the Universal Datagram Protocol, and there's a very, very fundamental difference between these two protocols. TCP is reliable packet delivery. There's a lot of checks and balances and acknowledgments, and if packets don't get there, and if they don't get there, in exactly the form they were sent, things are going to be retransmitted. There's going to be checks, etc. UDP, it's a best effort protocol. It's going to send the packet and basically hopes that it gets there, because it knows that if it doesn't get there, the time it's going to take for it to decide it didn't, deal with acknowledgments, retransmit, by the time it does all that, the packet's too late anyway. So there's really no reason to do all of the TCP checks. So that one fundamental difference, right? Reliable packet delivery versus a non-guaranteed delivery system. Another key difference in the data is looking over to the size bar, to the size of the packets. We see that the packets from the VoIP side are all small. Number one, 218 bytes, pretty small, and they're all exactly the same size, small and consistent packet sizes. On the data side, the packets are all over the place, large, variable sizes, another very significant difference. And lastly, looking at the delta time. So what this column is showing is it's showing the relative time between packets. So looking at it on the VoIP side, what we're saying is in that first 1.018, that was 18 milliseconds from the first packet to the second packet, and then 21 milliseconds from the second packet to the third second, 20 milliseconds, 19 milliseconds, 20 milliseconds, 20 milliseconds, 20 milliseconds. So what you see there is a very, very regular packet spacing. Compare that on the data side, right, where, again, they're all over the map. We're 321 milliseconds for the first one, and then 500 microseconds for the next one, and then 50 milliseconds, 55 milliseconds. It jumps all over the place. Another key difference between VoIP and data. So hopefully that and it gives you, at least from a packet perspective, a good feel there. So when it absolutely, but the point we're starting to make here is that there's that real-time nature to VoIP is very, very critical. And there are key issues on the network that happen all the time: packet loss, latency, jitter. They're all just part of packet transfer on the network. But real-time protocols are far more sensitive to these issues. And I'm going to dive into each one just a teeny bit here. Latency, that's basically the amount of time it takes for the packet to transit the network from one handset to the other. Sounds straightforward, but it's not, right? There's latency in general, even if the phones were directly connected over a hard wire. There's the time it takes the packets, basically the electrons at the lowest level that are underneath this communication to propagate across that wire, right? So to propagate that wave, or when we look across the wire. But there's more than that, right? Packets have to go through switches and routers, and they go through the internet. And in each one of those, not only is there that wire latency, but there's also things like queuing latency and decision latency and encoding and decoding latencies and compression and decompression latencies. Jitter buffer, which we're going to talk about jitter in a second. All of those add up to causing an overall latency from one end to the other. And as you see with the little thermometer, the ITU recommends really no more than a one-way delay of 150 milliseconds for VoIP. And it would be pretty similar for video as well. So 150 milliseconds of latency is not that much when you take all of those things into consideration. So latency can be a real big issue on the network. Again, with wired data, with a file transfer, maybe the file transfer is going to take longer because there's latency, and because the latency starts to cause problems. But you're just going to wait longer to get it. It's not like it can't be reassembled. It certainly can. Latency with VoIP does cause reassembly problems. Effects of latency, you're going to hear some talk over. You get this all the time, even on cellular calls today. You're probably very, very used to it. You think the user's done, and then you go to speak, but there was just enough latency that, now some more voice starts to come, and then you start kind of talking over each other, and it's just very uncomfortable. That's latency. And a lot of times you'll hear some echo as well. And I bring up these effects things to make the point that you don't always need to collect network packets and do analytical and go down to the voice to the level of analysis and calculations from a packet perspective to get a feel for what might be wrong in a unified communication session, right? Sometimes just listening and hearing these things will give you at least an indication as to what kind of problems you might be having. So talk over, probably latency. So it already starts to point you in the right direction before you've collected any packets, done any sort of analysis at all. Jitter is where the delivery of the packets becomes uneven. So we saw in the screenshots a few slides ago that we had very regular delivery in that VoIP conversation, right? Those packets really were about 20 milliseconds apart. Maybe there was a millisecond or so where they, some were 19, some were 21. Well, that's about a millisecond of jitter. It means that I'm not 100% at the 20 millisecond interval, but my variation over the interval is not very large, right? But that variation over the interval can become really large, and that's what jitter is. What there's always an attempt on the receiver end, because there's always going to be jitter introduced by all of those other network components that we mentioned on the latency slide. Jitter is, again, going to be introduced. So the receiver always makes an attempt with a buffer to leave enough space to be able to put things back in the right order, number one, and number two, to reset the intervals between those packets so that when they actually get delivered to the decoder, that there'll be that regular spacing again. But again, you can only do that within a certain budget, right? More than about 150 milliseconds, and you've introduced too much delay. So you can't have a buffer, that's maybe bigger than about 50 or 60 milliseconds, because you have to deal with the other latencies as well. So now anything that's later than that is just going to end up being a drop packet, and that's going to cause you problems. So definitely things to consider. Most jitter buffers today on the receivers are actually dynamic. They're not just set to a specific value, but just so you know. Basically, anything more than about 100 milliseconds, and you're just going to drop the packets. The effects, you'll kind of hear weirder kind of sound effects that vary, and some static, stuttering. If it's video, it might be jerky or irregular. Those are the kinds of things that come from jitter. And again, as I mentioned, if the jitter is too high, packet loss can result. And packet loss, of course, is you're just dropping packets due to either physical layer corruption or congestion when you didn't have adequate quality of service provided, or the jitter buffer, again, can't even place that packet in the right order anymore because the other packets that it needs to be around have already gone by, so it drops the packet. Packet loss effects, that's more like missing sounds, syllables, words, phrases. Typically the algorithms in the phones can deal with about 30 milliseconds of missing data, but more than that, it can't predict what the signals levels were between between the packets that it has, or between the data that it has, and then it just it's noticeable to the listener. Just to give you a feel, looking at some math there, if you drop 15 packets per second, you'd have a loss rate of about 30%, which would be huge for VoIP. And if you were to lose a number of consecutive packets in a row, it's about 15 packets to a whole word typically. So you don't need to lose. You lose half of those, you're still getting kind of weird syllable losses, and that's really very bothersome and troublesome for voice over IP users as well. And even a few packets makes a big difference. We really need to be looking at packet loss that's lower than 2% to really have a very high quality voice over IP communication. I'm going to just flip past these real quick because I'm going to show you OmniPeak in a minute and show you where we can find this detail. One other thing is kind of measuring that quality of experience of the user, and the way that's done is with some metrics. One's the mean opinion score. And the mean opinion score is a range from 1 to 5. It really started with an average opinion, hence mean opinion, where people actually listened to phone calls way back when in the plain old telephone system, and rated them. And then those became like the standards, the metrics that others were compared against. So again, a range of 1 to 5. Not all of the different encoding and decoding schemes can get all the way to 5, depending on the bit rates that they use. For example, G.711, the highest MOS score you can get is 4.4. Anything above 3.5 is good. Anything above 4 is quite good. R factor is another metric similar to mean opinion score, but comes from a different perspective. It comes from a very analytical perspective where it tries to use latency and jitter and packet loss and combine all that together into one quality number. It's a 0 to 100 range, and it comes in many flavors: listening quality, conversational quality, etc. So those are the metrics that we use, and we can also find those in OmniPeak as well. And I'm actually running a little bit out of time. So in terms of the ability of UC and TCP to coexist, I'm going to say that they can, but the one thing to remember about voice over IP is we can continue to introduce calls, but once we exceed the limit of our channel for VoIP, the quality really goes down for everybody, for all the calls. It's not like the last guy in suffers. Everybody suffers once we saturate whatever bandwidth we have there for VoIP. So it's a very critical element to keep in mind when even designing for and then analyzing unified communications. So managing the coexistence, you got to remember that quality is better than quantity when it comes to unified communications, and that's always the way to go. We tend to think of quantity a lot of times from a network perspective, 1 gigabit per second bandwidth, 10 gigabit per second bandwidth, but it's really the quality that matters much more. And understanding the characteristics of your network traffic is very important. Do you have bursty traffic, big spikes? That's definitely going to impact your VoIP. Or is it more prolonged, slow rises in utilization where your VoIP is able to address and adapt to that? So it's very important to have a baseline of your network traffic in general. And again, considering not only the averages over time, but even looking at spikes and even very short-term spikes. Millisecond spikes can really matter even on your data network. With that, I'm going to just real quickly hop into OmniPeak. I think if I slide across, you're also able to see OmniPeak. So several ways if I wanted to start to analyze voice over IP. I might first just want to start in an overall dashboard. And a dashboard like this is going to show me what's going on. Again, I'm going to use VoIP as an example of unified communications because it's one of the easiest ones to be able to understand and get some measurements for. And you can see we have an overall area here where there's call counters and call summary. We can see our total packet loss. I said, under 2%, is really better. Here we have voice packet loss that's at almost 5%, not so good. And you see we have a fair number to the right of that of bad calls. Almost 30% of the calls are bad, and that relates very much to that packet loss. You see below that a graph of call quality. I mentioned that mean opinion score, so we provide a graph of that mean opinion score across all of the different encoding and decoding schemes you might use. Now in your network, you're not going to have 10 different encoding schemes typically, but of course OmniPeak is able to handle all of the common encoding and even some of the uncommon encoding and decoding schemes, and then we're able to graph the mean opinion scores per encoding and decoding stream. For example, in the middle of the graph, you see, we were looking pretty good. We were up around 4, and then all of a sudden we had a drop to a minimum value of about 2 in the mean opinion score for a second. So, we know in the middle of that call, that would have been a point of very poor quality in that call. Below it, just seeing the number of calls, and then below that, at the bottom, call utilization, where we're actually graphing the real-time packet utilization or call utilization against network utilization. So in this case, it's all VoIP traffic, but in other cases, we would see it very much more of a mix in our VoIP traffic. If we want to go a level deeper, we can go into our calls view where we're actually able to list all of these calls call by calls. And let's say we are trying to do some troubleshooting. Well, there's a few ways to go about that troubleshooting, right? We may, number one, say, you know what, I'm interested in my mean opinion score. I know that's important to me. I want to go over and sort so that I can quickly find the calls with the lowest mean opinion scores because those are my problems. And I go ahead and do that, and I see here's call number 16 had a low mean opinion score, so somewhere in the call it dropped to 1, which is horrible. And then a few more there where even in the 2 range, and you can see we also with the red dots over on the left annotate that call quality as well. So that's one way to quickly get to the root cause maybe of a problem with a call. Another way is to come down into what we call our expert event area. This is down toward the bottom. You see we have our event summaries, and there's a number of summaries that relate to VoIP. So first I can classify them all by VoIP. So now my VoIP experts are at the top, and maybe I want to see, boy, I already hit the low MOS scores. That there's those. Maybe it's I'm concerned that maybe things were not marked properly for quality of service. So I have an expert for that. I click on that expert, and then we're able to quickly find exactly where that call, which calls are not marked for quality of service. So it allows us to very, very quickly zoom in on particular issues. If I want to go a layer lower, I can go down to my media view, and now I'm looking at each one of the calls broken down by each direction, because direction matters a tremendous amount in VoIP communications, because the packets from the caller to the callee may not follow the same path as the packets in the opposite direction. So it's very important that we're able to do that. And again, I might see a click on where am I not marked for quality of service, and you see a number of my calls, right, are having problems where there are at least some packets in the call that aren't marked for quality of service. If I were to do that, find which ones are not marked for quality of service and see that many calls, that's indicating that there is certainly a problem, somewhere along my route and in one of the routers that is carrying the bulk of my VoIP traffic. So, we can very quickly start to narrow that down. If I want to get to even one last layer of detail here, I can go to one of my bad call segments here and double click on that call, and we get into a bounce diagram of that call where we can see packet by packet what went on in that call. So we see all the ones with the black lines that are indicated. Those are indicating the management packets, or the configuration and control packets to set up the call, and we see the order that they go in. And then in this middle area, you can see we have these thumbnail graphs of the actual data in the call, where we have little thumbnail graphs of the jitter, right, and the R factor, and we can see that within our call, and we can see, what our, for example, in this area right here, right, our jitter went up to 34 milliseconds. That's horrible for jitter. So again, we know this was a call with poor quality, and now we've already determined our poor quality is most probably due to jitter. So again, it gives us that indicator as to where to start looking on our network to do more detailed analysis. So with that, let me just summarize here. And I'm sorry I didn't get through quite all of the material, but I think what I was able to get through gives you a very good feel that that in the end, unified communication network data, the data itself that's going to go over the network for voice, video, etc., is fundamentally different than your traditional network data. The real-time notion of unified communications versus the non-real-time or the near real-time, aspect of more fundamental network data, file transfers, etc., application usage is really key here. Unified communications still remains one of the main concerns for network and IT engineers, and I'm sure that I made the point here that UC data is far more vulnerable to common network issues like jitter, packet loss, and latency than traditional data. And I didn't get into the wireless part, but the one point to make about wireless is that it's even worse with wireless, because wireless being a medium where you're not fully in control, where there can be interference on the medium, it makes the network issues, things like jitter, latency, and packet loss, even more severe when you're trying to transmit real-time data, real-time unified communications data over a wireless network. And troubleshooting unified communications really requires that you look at the network in total. You can't focus on just the UC or the real-time protocols in a vacuum. That is, what you get a lot from the vendors of, either individual UC products or unified communication systems in general. They'll give you a very nice dashboard that shows what is ongoing from a UC perspective. But when you really need to troubleshoot something and dig in, you need to see that unified communications data in relation to the rest of the data on your network. That's the only way you're able to fully troubleshoot and analyze unified communications data.